Hello there and welcome back to Backroad Tutoring. In this video we're going to be looking at atoms, nuclear radiation and its hazards. And this is video 2 of 3, so let's get right into it. Can you remember what an isotope is? An isotope is just an atom of an element but with different amounts of neutrons. This means it is still the same element, the proton number or atomic number hasn't changed, but it may be lighter or heavier. How might the amount of neutrons affect the mass number? Well, remember, the mass number is just the amount of protons and neutrons added up. So if there is a higher amount of neutrons, then the mass number will be higher. Isotopes can make some elements unstable. Remember, an element depends upon how many protons are found in the nucleus, not the amount of neutrons. This means that different elements have different amounts of protons in their nucleus. So different elements on the periodic table have atoms with different amount of protons in them. But isotopes of certain elements can be unstable. If there are too many neutrons in the nucleus, the atom tries to get rid of those neutrons. Too many neutrons in the nucleus means the atom is unstable. You don't need to know why, but you just need to know that it is. So if you have an atom with too many neutrons, then the atom wants to get rid of those neutrons and it wants to become more stable. Radioactive decay is defined as the process by which an unstable atomic nucleus loses energy in terms of mass in its rest frame by emitting radiation. But what does this actually mean? It means that unstable nucleus with more neutrons than it needs, emits particles in order to become more stable. So radioactive decay is where you have unstable nuclei getting rid of either protons, neutrons or electrons in order to become more stable. So properties of radioactive decay, it is completely random. So in this little animation here, you can see that there is a fission reaction which we'll cover later. It's completely random. There is nothing we can do to predict which nucleus is going to decay next. Completely random. So, we're going to have a look at the definition of nuclear activity. Activity is the rate at which a source of unstable nuclei decays. So, nuclear activity is the rate at which the source of unstable nuclei decays. Activity is measured in the becquerel, which is given units BQ. This is 1 decay per second. So, 1 becquerel is 1 decay per second. That means 3 becquerels is 3 decays per second. So remember, activity is just how much unstable nuclei give off radiation in a period of time per second in the case of becquerel. Count rate is the number of decays recorded each second by a detector. And an example of a nuclear radiation detector is a Geiger-Müller tube. And that's shown here. So this is what a Geiger-Müller tube looks like. So if you point this tube at a radioactive substance, it will measure the counts. It will measure the counts of decays, or the amount of radiation which comes off that radioactive source. So unstable isotopes, those with more neutrons than what is stable, release radiation. This is often considered dangerous and is given this warning symbol. So when you see this warning symbol in the lab or in a manufacturing plant or something like that, it means there's nuclear radiation and that is potentially very dangerous. So we're going to have a look at the definition of ionization now. Ionization is the process where atoms lose or gain electrons, giving them a positive overall charge or a negative overall charge, and this can be dangerous to human organs. So ionization is where atoms lose or gain electrons, and if you lose and gain electrons, you're going to get an overall charge because electrons have a negative charge. So if you lose some electrons, if you lose some negative charge, you're going to get an overall positive charge. If you gain electrons, if you gain negative charge, you're going to have an overall negative charge, and ionization is dangerous to human organs. The first bit of nuclear radiation that we are going to cover is alpha particles. So an unstable isotope can emit an alpha particle. This consists of 2 protons and 2 neutrons, which is exactly the same as a helium nucleus. So if you think of the element helium, it has 2 protons and 2 neutrons, and that's exactly what an alpha particle is, 2 protons and 2 neutrons. An unstable isotope can emit an alpha particle. So alpha particles can't travel very far and don't penetrate through materials very well. They can't even get through paper. So alpha particles don't travel very far, although they are possibly the most dangerous because they have the highest ionizing power. So remember, ionization is where you knock electrons out of the shells, or even you might even gain electrons, and alpha particles are the most dangerous in terms of ionization power, because they do the most ionization. Unstable atoms with more than the required amount of neutrons lose 2 neutrons, making it more stable. So because an alpha particle is made of 2 neutrons and 2 protons, you can see that there's 2 neutrons leaving the nucleus, and because isotopes with more neutrons than what's needed are unstable, that's very good for the atom. It gets rid of 2 of those neutrons. You don't need to know why 2 protons are lost too, but they are. So you just need to know an alpha particle consists of 2 protons and 2 neutrons, and an unstable nucleus wants to get rid of an alpha particle because it's getting rid of 2 neutrons, and those neutrons made the atom unstable, and now they're gone. So the atom is now more stable. So the next bit of nuclear radiation that we're going to look at is beta particles. So an unstable isotope can emit a beta particle. This consists of 1 electron. Beta particles can travel a medium distance and penetrate through some materials like paper. So beta particles can travel a little bit further than alpha particles, and they can penetrate through a little bit more than what alpha particles can. They can actually go through paper. Beta particles have moderate ionizing power. So not quite as much ionizing power as alpha particles, but still a fair amount. So beta particles, they can travel through a little bit more, and they're a little bit more ionizing. Unstable atoms with more than the required amount of neutrons split 1 neutron into a proton and an electron. This causes 1 more proton to stay within the nucleus and 1 more electron to be present. The electron flies away from the nucleus as radiation. Finally, an unstable isotope can emit energy. This energy is in the form of an electromagnetic wave, as seen here, the gamma ray. Gamma rays can travel very far and are very penetrating, so gamma rays can go through paper and they can even go through plastic. But gamma rays have very little ionizing power, so despite the fact that they can travel further and through more things, when they actually get to a person or a thing, they don't ionize as much as beta particles, or anywhere near as much as alpha particles. So unstable atoms which have just went through nuclear fission or fusion, which we'll cover later, often need to release a large amount of energy. Gamma rays are the highest energy electromagnetic wave, so there is no better way to release energy than via gamma rays. Gamma rays aren't a particle. That's something you really need to hammer into your heads. Gamma rays, unlike beta and alpha decay, are not particles. They are an electromagnetic wave, and we'll cover waves later on in our course, but just know gamma rays, not particles, they are waves, very high energy waves. So if you have a nuclear reaction and you need to get rid of a lot of energy very quickly, gamma rays are ideal. So gamma rays are emitted after nuclear changes. So alpha decay. This little animation that we've just seen there shows how alpha decay works. So let's say you had a particle and you had a group of protons and a group of neutrons. Let's say there's too many neutrons there. It's an isotope with a lot of neutrons. It's radioactive, okay? It would be that nucleus's benefit to get rid of those neutrons because it would make it more stable. So it does, and when those 2 neutrons go away, 2 protons go away with it. So atom gives off 2 protons and 2 neutrons, making it more stable. There are less neutrons within its nucleus. So beta decay next. You can see that a neutron splits and becomes a proton and an electron, and the electron is fired away. So atom splits a neutron into a proton and an electron, the electron flies off. So beta decay, you have your neutron, which is, there's no overall charge, it's neutral, and what actually happens is the neutron splits in 2 into an electron and into a proton. The proton stays in the nucleus and the electron flies away. and that is the beta particle. The beta particle is the electron. And gamma radiation, you have a nucleus and it needs to get rid of a lot of energy quickly. So it gives off this gamma ray, which is a high energy electromagnetic wave. The atom doesn't give off any particles, instead energy in the form of a wave, gamma rays. If you're following along in your revision workbook, pause the video now and complete task number 4. Okay, next we're going to have a little look at nuclear equations. Nuclear equations are used to represent radioactive decay. So we've had a look at alpha, beta and gamma decay, and all of these can be represented in equations. Each particle can be given a different symbol. Remember, these particles are alpha and beta, as gamma radiation isn't a particle. So in these nuclear equations we're going to look at alpha particles and beta particles, but we don't look at gamma particles because they don't exist. Remember, gamma radiation is just a wave. So, alpha particle symbol. The alpha particle symbol is this. He, 4, 2. A helium atom, as this is actually what an alpha particle is, except it has no electrons. So, remember, an alpha particle is 2 protons and 2 neutrons. So you have 2 protons and 2 neutrons, and that is what an alpha particle is. But remember, we don't have any electrons on this alpha particle because it's not actually an atom, it's just an alpha particle. But we represent it as a helium nucleus because it has a mass number of 4, because there are 4, we have 2 protons and 2 neutrons, which give a mass number of 4, and it has an atomic number of 2 because there's 2 protons. So an alpha particle symbol is given as that, a helium nucleus. The beta particle is given this symbol, an E with a mass number of 0 and an atomic number of -1, as the E represents an electron with proton number -1. Because remember, in a way, an electron's a little bit like a negative proton, isn't it? Because an electron has a -1 charge, whereas a proton has a +1 charge. So the proton number here is -1. It has a charge of -1. But remember, electrons have a mass which is very, 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 very small. So we actually say it has a mass number of 0. Mass number of 0, proton number -1, and the letter we give a beta particle is E, because it is an electron. So that's the symbol for a beta particle. So what actually happens after alpha decay? Well, after alpha decay, the nucleus becomes more stable. Remember, that's the goal. The goal of nuclear decay is for the nucleus to become more stable. So after alpha decay, the nucleus becomes more stable because it's lost neutrons. It has also lost protons, meaning it has actually become another element. Remember, the protons is what makes up the atomic number, and that's what makes up the element. So if you lose a proton, or lose 2 protons in this case, you're actually changing the element that it is. For this, we use a nuclear equation as shown on the next slide. So the emission of different types of nuclear radiation may cause a change in the mass or the charge of the nucleus. Let's take this for example. Here we have radon, which is decayed. It has emitted an alpha particle, shown on the right, but notice how the numbers on the top and bottom all add up. So let's say we start with a radon atom, or a radon nucleus. Radon has a mass number of 219, and it has an atomic number of 86, and that's because, remember, there are 86 protons in the nucleus, and protons an atomic number, same thing, so there's 86 protons, the atomic number is 86. And the mass number is 219, and that's because there are 219 protons and neutrons in total. Okay, so this isotope is unstable. It wants to get rid of some neutrons to make it more stable. So in order to get rid of those neutrons, what it does is it emits an alpha particle, and remember, this is the symbol for an alpha particle. So it emits an alpha particle and gets rid of 2 protons and 2 neutrons. If you're getting rid of 2 protons, the atomic number goes down by 2. So what you get is you go from 86 as an atomic number to 84. But because you're getting rid of 2 protons and 2 neutrons, the mass number comes down by 4. So before we had a mass of 219, now we have a mass of 215. So what we get is we get an isotope of polonium with an atomic number of 84. This is how nuclear equations work. When particles decay, they often change into other particles, and because they have a different atomic number, they've changed element. This is how alpha decay works. The particle which is created moves 2 elements down from the initial nucleus. So, just to clarify that really quick, remember, when alpha decay happens, you're getting rid of 2 neutrons, which is the goal to make it more stable, but you're also getting rid of 2 protons. And remember, it's the amount of protons which determines which element that atom makes up. So by getting rid of 2 protons, you're changing the element that that atom makes up, and you're moving down the periodic table 2 spaces. So the initial nucleus was a radon nucleus, which is here on the periodic table. But because we've lost 2 protons, we've gone down 2 spaces in the periodic table, and we've ended up with polonium. Ending up as a polonium nucleus as it has lost 2 protons. It has lost 2 neutrons, meaning the mass number decreases by 4. And just to go back over this, if you notice the numbers in this equation, they all add up. 219 on the left side of the arrow, well, that's the same as 215 add 4. 86 on the left-hand side of the arrow, well, that's the same as 84 plus 2. So in the exam, it's quite useful to know that on both sides of the equation, the total amount of mass and the total atomic numbers are the same. So, let's move on to beta decay now. After beta decay, the nucleus becomes more stable because it's lost neutrons, and remember, that's the goal of decay, of radioactive decay. This is because one of the neutrons has split and became a proton and an electron, but the electron is fired away, so it's lost 1 negative charge. As it has lost a negative charge, it is now more positive after the beta particle is gone. So, this little animation there, that showed how beta decay works again. You have a neutron, splits into a proton and an electron, and the electron is fired away. But the electron is fired away, so it's lost 1 negative charge. As it's lost a negative charge, it's now more positive after the beta particle is gone. So once that electron or the beta particle has gone, it's actually gained charge because it's lost a negative charge. So for beta nuclear equations, we can write equations again. The emission of different types of nuclear radiation may cause a change in the mass or the charge of the nucleus. For example, an isotope of carbon, carbon-14 we'll call it because it's got a mass number of 14, undergoes beta decay. So here we have a carbon-14 which has decayed into nitrogen, but notice how the atomic number has went up. It's actually received it's went up in charge. It's more positive after losing an electron. So we have our carbon nucleus here with a mass number of 14 and an atomic number of 6. When we lose an electron, when we get rid of an electron, remember that the neutron in the nucleus has split. It's split into a proton and an electron. When the electron goes away, well, that's represented here, but it leaves behind a proton. So what you're actually doing is you're actually giving it another proton, and remember, it's the proton which makes the atomic number. So what you're actually doing is you're taking this carbon nucleus and you're giving it another proton. The atomic number goes up by 1. And the atomic number going up, well, that means it's a different element. So you find that the carbon atom changes into a nitrogen atom or a nitrogen nucleus because you're giving it another proton, and the proton changes the atom, which therefore changes the element which that atom represents. This is how nuclear equations work. When particles decay, they often change into other particles, and because they have a different atomic number, they've changed element. This is how beta decay works. The particle which is created is 1 element up from the initial nucleus. It has gained 1 proton, moving up the periodic table. As remember, the periodic table is in order of atomic number. So that's shown here. The initial nucleus was a carbon nucleus. Ended up as a nitrogen nucleus, it's gained 1 proton and lost 1 electron. But electrons have virtually no mass, so the mass number does not change. Yes, you are losing this electron, but because that has such a small mass, we discard it. So the mass number stays the same. Mass number does not change, but the atomic number increases by 1. So because our atomic number is going up by 1, we move 1 up the periodic table, and we go from carbon up to nitrogen. So remember, alpha decay, we go down the periodic table 2 spaces. Beta decay, we go up the periodic table 1 space. And that's to determine what goes on the other side of the arrow. But remember, if we're going through beta decay, you have to add this symbol, an electron with a -1 atomic number and 0 mass number. And if we're going through alpha decay, you have to add our helium nucleus, He, with a mass number of 4 and a proton number of 2. The final nuclear equation, which is by far the easiest, is gamma nuclear equations. Gamma rays don't change the composition of the nucleus. No particles are lost or gained, as remember, gamma rays are not particles. So during gamma decay, or if you can call it that, during the time when gamma rays are radiated, we get a very simple nuclear equation. Whatever's on the left-hand side is the same on the right-hand side, because our radon doesn't change, it doesn't gain any protons, it doesn't lose any electrons, the amount of neutrons stay the same, so the mass number and proton number both stay the same. So that's a very easy thing to remember for the gamma. Nuclear equations, further information. So alpha particles can also be portrayed as symbols like this. This is the Greek letter for alpha. So when we're talking about alpha particles, we either show them as this, an alpha particle, or a helium. Beta particles can also be portrayed as symbols like this. B for beta, the Greek letter for beta. That should say Greek, not green. Sorry for that little typo there. So when we write beta particles, we either write them as this, the beta symbol, or we write it as an E for an electron. So bear that in mind. Alpha particles could be shown as alpha, the Greek symbol, or and beta particles could be shown as a beta, the Greek symbol. Nuclear equations practice. Let's go through these together. So, Neptunium-237, that decays by alpha emission. Okay, so this, let's say this was in an exam. This exam's been quite nice to you because it's actually given you the element which it decays to. Sometimes that might not be there and you have to look it up on the periodic table yourself. Remember, alpha emission, we go down the periodic table 2 spaces. So neptunium decays to this. So if we have alpha emission, we know that we have lost 2 protons. So our proton number was 93, but now it's 91. Remember, alpha emission is 2 protons and 2 neutrons, and protons and neutrons go towards the mass number. So if we've lost 4 of these in total, our mass number reduces by 4, leaving us with a mass number of 233. Okay, so remember, we know that both sides of the equation have to have the same mass and the same number of protons. So 233 plus something is 237. Well, that's 4. We know that alpha particles have a mass number of 4 because they're 2 protons and 2 neutrons. 91 plus something is equal to 93. Well, that's 2. And that makes sense because alpha particles have a proton number or an atomic number of 2 because there's 2 protons. Hydrogen-3 decays by beta emission. So we have hydrogen with a mass number of 3 and an atomic number of 1. Okay, so that decays into a helium nucleus. Remember, through beta emission we go up the periodic table 1 place. So we know that we have a proton number or an atomic number of 2. When we have beta emission, our mass number stays the same because the emission of an electron gets rid of virtually no mass. So our mass number stays the same. Remember, a beta particle has an atomic number of -1 and a mass number of 0. And this makes sense because 3 plus 0, well, that's just the same as 3. 2 plus minus 1, well, that's just the same as 1. So that makes sense. If you're following along in your revision workbook, pause the video now and complete task number 5. Moving on. Now we're going to have a look at the nature of radioactive decay. The nature of radioactive decay is said to be random and spontaneous. Random means made, done, or happening without method. This illustrates nuclei decaying. Anyone could decay, and to our understanding it is completely random. So we can't predict which nucleus is going to decay next. We can't predict it. It's just completely random. The next thing that radioactive decay is said to be is spontaneous. Spontaneous means there is nothing we can do to change it, or there is no conditions we can create in order to stop the decay of nuclei. So spontaneous, that means there's nothing we can do to stop or change radioactive decay. We can't change the setting, we can't change anything about the settings of where this thing is to change the nature of radioactive decay. So we can't sort of, I don't know, put it in a dark room and hope it doesn't decay. We can't shine lights on it and hope it doesn't decay. It's spontaneous. There's nothing we can do to change radioactive decay. A question asking about these two words makes for a fantastic 2-mark question. It's incredibly important that you remember these two words and, of course, what they mean. So, in a 2-mark question, this could say, describe the nature of radioactive decay. First thing you think of, random and spontaneous, and what they mean. So, nuclear decay is random, as shown by this graphic below. We can't tell when or which nucleus is going to decay next. So, it's random, we don't know when. We've already been through this. However, we can take an average. We can take an average and work out how long it takes for the amount of nuclei to decay to half the original amount. So if you have a number of undecayed nuclei, we can take an average and work out when half of those undecayed nuclei decay. This is known as half-life. In one half-life, the amount of undecayed nuclei reduce by a half, and the new nuclei replace them. So after one half-life, which is a period of time, the amount of undecayed nuclei is reduced by a half. We can introduce a clock. Can you work out the half-life? So after 4 seconds, 50 of the 100 remain. After 8 seconds, 25 of the 100 remain. After 12 seconds, 12 remain. Do you notice a pattern here? And after 16 seconds, 6 remain. So, every 4 seconds, the amount of undecayed nuclei is reducing by a half. Because, as we started with 100, after 4 seconds, well, there's 50 left, and 50 is half of 100. And after another 4 seconds, there's 25 left, and 25 is half of 50. And after another 4 seconds, there's 12 left, and 12 is around half of 25. So, what do you think the half-life is? Well, 4. Every 4 seconds, the amount of undecayed nuclei reduces by a half. This means the half-life is said to be 4 seconds. The activity reduces by a half every time a half-life passes. This means that over 2 half-lives, the activity will have quartered, and that after 3 half-lives, it will be 1/8 of the original value. And we can have a look at this, and we can work out what the activity is after a certain amount of half-lives. So the initial activity of carbon-14 is 60,000 becquerels. After 2 half-lives, what is the activity? Okay, so the initial activity is 60,000. The activity after 1 half-life is just half the activity. So that would leave us with 30,000. The activity after 2 half-lives, well, that's just half again. So 30,000 divided by 2, that's 15,000. And the units for activity are in becquerel. So our final answer is 15,000 becquerels. There's a little shortcut you can use though to work out the activity ratio after a certain amount of half-lives. The ratio can be worked out by this very simple formula, 1 over 2 to the power of n, where n is the amount of half-lives. For example, after 3 half-lives, you would use this ratio. 1 divided by 2 to the power of 3 is equal to an eighth. So after 3 half-lives, you raise 2 to the power of 3, so the activity will be 1/8 of the original activity. So here's a worked example. The initial activity of carbon-14 is 60,000 becquerel. After 4 half-lives, what is the activity? So the activity ratio we know is 1 over 2 to the power of n. 1 over 2 to the power of 4 because it's after 4 half-lives. So the activity ratio is 1 over 2 to the power of 4, which is 1 over 16. So to find the activity, we just multiply that ratio by the original amount and we get 3,750. And the units for activity are in becquerel, so my final answer is 3,750. If the question asked about what would be the activity after 5 half-lives, we would just replace this 4 with a 5, and it would be 1 over 32. And then you would just multiply 60,000, because that's our original, by 1 over 32. It's really that simple. If you're following along in your revision work, you can pause the video now and complete task number 6. Okay, so next we're going to look at radioactive contamination. Radioactive contamination is where unwanted radioactive atoms are present within something else. For example, someone who works in a nuclear power station may get uranium, which is still decaying, stuck in their work clothes. When coming home, this may be radiated and cause problems. So contamination is where radioactive substances move somewhere where they shouldn't be. So if you work in a place where radioactive substances are, for example, a nuclear power station, and you get some radioactive substance on your person, and then you leave the factory, well, you've become contaminated because you've got some radioactive materials or some undecayed nuclei on your person. And that's radioactive contamination because it's not really supposed to be on you, it's supposed to be in the factory. And obviously radioactive materials are quite dangerous, so you have been contaminated with radioactive material. Irradiation, that's different. Irradiation is where someone is harmed by radiation. Like if the worker then went home and the uranium decayed and some of the alpha, beta and gamma radiation went on to someone else or something else. The person or object which has had alpha, beta, gamma particles hit it is said to be irradiated, but it is not contaminated, as this object/person isn't actually radioactive themselves, they've just been affected by it. So if that radiation on that worker, or if that worker was to go home and talk to, let's say, his brother at home, and his brother was hit by some of that radiation which has been emitted by those particles on his body, then he is being irradiated. He's not contaminated because there's no radioactive particles on his person, but the radiation has hit him, so he's been irradiated. So the difference between irradiation and contamination is where radioactive particles are somewhere where they shouldn't be. Irradiation is where something's been hit by radiation and affected by it. There are hazards associated with contamination and irradiation. Radiation can be ionizing. It can cause charged ions to form from normal atoms through gaining and losing electrons and protons. Ionization can be dangerous as it can increase the chances of getting cancer. You can shield to protect yourself from harmful radiation. The use of specialist clothing can shield you from harmful radiation. Lead can act as a shield to harmful radiation. So if you go to, let's say, a nuclear power station or something like that where nuclear radiation is used, often you will see people wearing like lead lining. And that stops harmful radiation from getting through and irradiating them. So lead is a good barrier to stop you being irradiated from radiation. You can also monitor radiation. So you can monitor radiation by using a radiation detector. Precautions need to be put in place if radiation is high, and more needs to be found out about the harms of radiation, so scientists can peer review it and make new statements. So radiation at the minute, it's one of those areas in science where people are still actively researching and people are still finding out things about it, because radiation can be quite useful. You know, it's used in power stations and stuff like that. But it can also be very dangerous. And one of the reasons why we don't know a lot about what it can do to people are because we know that exposing people to radiation is very dangerous, which makes experiments not very humane. There's been nuclear disasters like Chernobyl and like Fukushima, for example, where people have been affected by radiation and people can examine what happens to people after they've been irradiated. But actually doing tests on people, well, that's quite inhumane. That's one of the reasons why we don't know a lot about radiation and its effects. Remember the ionizing power of these three types of radiation? Alpha is very ionizing, however it struggles to penetrate through human skin. Beta is moderately ionizing, however can penetrate through human skin a little more easily as compared with alpha. Gamma is not very ionizing, but very dangerous as it can penetrate human skin and enter the body very easily. The half-lives of radioactive substances also make a difference to the level of risk associated with them. This is because the activity, which remember is the amount of decays and radiation which is coming off of something per second, is much higher for elements with shorter half-lives, until of course they run out and have stopped decaying or have nearly finished decaying. So if you have an element or an isotope of an element which has a very, very short half-life, well, that's more dangerous, because if it has a short half-life, it's given off more radiation in a short amount of time. So elements or isotopes of elements with short half-lives are more dangerous than those with long half-lives, because if you're exposed to something with a long half-life for the same amount of time as you are exposed to something with a short half-life, well, the thing with a longer half-life, you're gonna get irradiated by that much, much less than you are with something with a shorter half-life. Short half-lives mean more radiation is given off in a shorter time, putting more people and objects at risk of being irradiated. Longer half-lives mean it takes much longer for the same amount of radiation to be discharged, and therefore, within the same amount of time, much less is given off. And the stage at which the radioactive material is at, that also makes a difference. Look closer to the present, the closer to the present, the more dangerous the radioactive substance is, as more radiation is being given off per unit time than in the future. So if you take right now as a time scale, if you look at right now, and you say that at this point in time, today, this amount of radiation is given off, 100%, well, after 5 years, which is the half-life of this material, it drops to a half. And then after 10 years, which is 2 half-lives, it drops to a quarter, 25%. Then after 15 years, 3 half-lives time, it drops to 12.5%, so on, so on, and so on. So look at the amounts of radiation which is given off now and in 25 years. In the first 5 years, this much radiation is given off. So, in 5 years from now, half of the undecayed nuclei will have decayed, and that means half of the undecayed nuclei will have given off potentially dangerous radiation. But then, in the next half-life period, less is given off, then less, and then less. So if you take these sort of bars and put them together, you can see the amount given off for every half-life which passes by reduces by a half. So in later stages of decay, far away from now, less radiation is given off, and therefore there is a smaller chance of being irradiated. So the longer you leave it before you expose yourself to radiation, the safer it is. If you're following along in your revision workbook, Pause the video now and complete task number 7.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.